Hello everyone. In this video we're going to look at the second law of thermodynamics, which is probably the most important and far-reaching idea in the entirety of thermal physics. We're going to look at how it was first derived and formalized with the concept of heat engines, heat transfer and work. Now nowadays we understand the second law to really all be about entropy, and in the last couple of videos we've laid the groundwork for formalizing what entropy is. But before we actually go on to do that, I think it's really important to see how the second law was discovered and formulated without entropy, because it was this second law that inspired the derivation of entropy in the first place. And although we will derive entropy in terms of probabilities and statistical mechanics, it's really useful to see this because the first definition there was of entropy was in terms of heat and heat transfer and temperature. And even though we will derive the statistical one, there's no one true derivation of entropy. It's useful to see entropy in lots of different lights, and I will talk about that a bit more at the end of the video. So even though the second law, as we will see here, relates to heat transfer and heat engines and work, it has much more wide-ranging ideas contained within it. And we will see in subsequent videos that this second law has impacts on information theory and cosmology, and we can make statements about the whole universe just by this second law. But first, we need to discover what the second law actually is and how it was first formulated. So, the first statement on the second law is written in this top box up here, and this was the statement as made by the physicist Clausius. And what Clausius said was, no process is possible where heat, represented by the letter Q, flows from a colder body to a hotter body in isolation. Now, what does that mean? Well, we know that when we touch something hot, our hand gets burnt, and that is because heat flows from the hot object into our hand. But the reverse of that is never true. We never touch a really hot stone and find our hand getting colder because heat is leaving our hand and flowing into the stone. And that's exactly what this statement says. It says that you will never have a process where the sole result is that heat is transferred from a colder body into a hotter body. Now you might say, well, what about my fridge? Because that sucks heat out of an already cold space to make it colder and ejects that heat out into the room, and that's fair enough. But I point you to these two words, in isolation, which are really important, because in order for a fridge to work, in order to do that process where we suck heat out of a cold body and eject it into a hotter one, we need to pay our electricity bill, we need to put energy into the system, we need to put work into the system. So if you take that out, if you have an isolated system where you can't put energy in, you can't do work on it, then it is never possible to have heat transferred from a colder to a hotter body. There is nothing we can do in this universe to make that so. So that was the first statement of the second law, and that was by Clausius. Now, a little later, there was a second statement of the second law, and that was by the physicist Lord Kelvin. Now, Kelvin, you might remember, is the name of the metric of temperature. Temperature is measured in Kelvin. So Kelvin had a lot to say about thermal physics, and he had a lot of influence in all different areas. But Kelvin's statement of the second law is as follows. No process whose sole result is the complete conversion of heat into work is possible. Now, that means that we can't have an engine, we can't build a contraption or a device which sucks out heat and then perfectly efficiently converts it into work. We can't have an engine where we shovel coal in, it creates a bunch of heat, and that perfectly drives a piston really 100% efficiently. There will always be extra heat ejected from that system. So we have these two statements here. One, it's not possible to transfer heat from a colder to a hotter in isolation. And two, we can't transfer heat into work with 100% efficiency. Now those seem like related, but not equivalent statements, right? They seem to make statements about different things. But what we're going to show in this video is that these two statements are perfectly equivalent, and that is what I intend to prove next. So, in order to prove the equivalence of these two statements of the second law, we first need to introduce the idea of a Carnot engine. Now, a Carnot engine was introduced by the physicist Sadi Carnot, and he was able to demonstrate that his type of engine, which I'm about to show you, is the most theoretically efficient type of heat engine that's possible, and that any other type of heat engine would violate this Clausius statement of the second law. Now, I don't intend to go through a whole proof of that now, but if that's something you'd like to see, please leave a comment below, and if there's enough demand, we'll cover that as well. But basically, what a Carnot engine is a Carnot engine has one reservoir, which is a really big body, which is held at a very high temperature, which I write as TH. And then another reservoir, another really big body, which is held at a low temperature, and that I write as TL. And what the engine does, which I draw here as a circle, labelled E, is it sucks heat out of the hot reservoir, which I write as QH, and it ejects heat into the cold reservoir, which I label QL, and as a byproduct, it does some work, which I label W. So you can think of this, an example of this is in a steam engine. So in a steam engine, we shovel coal into the furnace and we create a really hot furnace. That is our hot reservoir, TH. We create a boiling hot furnace. And then the engine, steam is created and that drives all these pistons in the engine. That is the equivalent of us doing work. So the really hot reservoir ejects heat into the engine and then the engine does mechanical work. But you'll also notice on a steam engine that there's a big plume of steam coming out the top. That is this heat, QL, which is being ejected into the atmosphere. And the atmosphere here is our lower temperature reservoir. So a steam engine is a perfect example of a Carnot engine. You have a hot reservoir and a cold reservoir, and the engine sucks heat out of one, ejects heat into the other, and as a byproduct does some form of mechanical work. And it's also worth pointing out that Carnot engines are theoretically perfectly reversible. So instead of doing it this way, we could do it where the Carnot engine, we put work in, so we put work into the engine. I have an arrow going into the engine to signify that we're putting work in, and as a result, we are able to take heat out of the cold reservoir and inject it into the hot reservoir, right? Carnot engines are perfectly reversible in this manner. And indeed, an example of this is your refrigerator at home. We put electrical work in, electrical energy in, and we take heat from the cold reservoir of the fridge and we eject it into the hot reservoir of the surrounding room. So that's the concept of a Carnot engine. And what we're going to do next is use that concept in order to demonstrate the equivalence of these two laws. And the way we're going to do that is, first, I'm going to assume that Kelvin's law is not true, and that will imply also, we'll see that Clausius's law isn't true, and then I'm going to do the reverse. I'm going to assume that Clausius's law isn't true, and we'll show that that is the same as saying that Kelvin's law isn't true. So, let me direct your attention to this diagram over here. Now, this diagram is like the Carnot engine diagram we saw earlier. So up here, we have the hot reservoir, a really hot body at constant high temperature TH. And down here, we have the cold reservoir, which is at a constant temperature of TL. And this E here is our Carnot engine. And like we showed in the second example, here we are putting work into the engine and we are drawing some heat out of the lower temperature reservoir, which is QL, and we are ejecting some heat into the higher temperature reservoir, which is QH. And then to complete this diagram over here, this KV stands for a Kelvin violator. It is an engine which violates Kelvin's formulation of the second law. Now, Kelvin's formulation of the second law says it is not possible to have an engine which sucks out heat and then converts that perfectly efficiently into work with no other heat loss. And that's what we see here. We have this amount of heat, QH prime, going from the hot temperature reservoir into our Kelvin violator, and then we have a perfectly efficient output of work, W, and we have no corresponding heat loss. There's no QL prime, there's nothing here. So this heat gets formed perfectly into work, perfectly efficiently into work, and gets driven into our Carnot engine, which works just as we described earlier. Now, let's apply to this the first law of thermodynamics, which we saw in a previous video. Now, the first law of thermodynamics says that the change in internal energy of a system, delta U, is equal to the heat we put into it, delta Q, plus the work we put into it, delta W. This is the first law of thermodynamics. So this is the heat we put in and the work we put in. If we are taking heat out, if we are taking work out, then these are negative. If we're putting heat in, if we're putting work in, then these are positive. So from that statement of the first law, we can first look at this Kelvin violator, and we can say that QH prime is equal to W. So it's perfectly efficient. All the heat we are getting in, all that heat QH prime is being transferred into the work. So the work is exactly equal to the heat we put in. QH prime is equal to W. And we can also say, by looking at this one, that that QH, the energy we are putting into the heat reservoir, well, that is equal to the energy we are putting into this engine, because we're taking QH out, and the energy we're putting in is W plus QL. So the first law tells us that. So now let's look at the net amount of heat we are putting in to this top reservoir, right? So we are putting in QH and we're taking out QH prime. So the net amount of heat we are putting in is equal to QH minus QH prime. And I'm now going to substitute these equations in here. So QH is W plus QL, and QH prime is W, so we have a minus W. And that is equal to QL. But hang on a minute, because now we have said that we are taking heat QL out of the lower reservoir, and that is the heat we're getting out of the lower reservoir, and that is equal to the net amount of heat we are putting into the higher reservoir. And lo and behold, that is exactly what Clausius says we are not allowed to do. This system is in isolation, right? We are not putting in work from an external agent into this system, and the net effect of this system is to transfer heat QL out of the cold reservoir and eject it into the hot reservoir. We have transferred heat from a colder to a hotter, and we have done it in isolation. By violating Kelvin, we have violated Clausius. Right, so now all that's left to do is prove that if we violate Clausius, we also violate Kelvin. And let me clear some space and then we'll do that. Right, so I've now changed this diagram around a bit, and instead of KV, I have this CV here, which is a Clausius violator. Come on to that in 1 second. But here I have a Carnot engine, except this time I have the Carnot engine taking heat in from the high temperature reservoir, QH, ejecting some form of work, W, and then ejecting heat into the lower temperature reservoir, QL. So this is just like the steam engine example. And then this Clausius violator, what it does is I've set it up to take exactly the heat QL out of the cold temperature reservoir, which this Carnot engine is putting in, and eject that heat perfectly efficiently into the hot reservoir. So we have QL coming out of the cold and QL going into the hot. And that violates this statement of the second law because there's no work being put in. So this is what's called a Clausius violator. So then what do we have here? Well, we have that there is no net change in the heat going into the cold temperature reservoir. We are taking QL out of it with the Clausius violator. We are putting QL into it with the Carnot engine. So the net result is that we are taking heat out of this hot reservoir, and what we are taking out is QH minus QL, and we are converting that solely into work because there is no net input of heat into the lower temperature reservoir. So all we are doing is taking this heat, QH minus QL, and converting it perfectly efficiently into work. And lo and behold, that is an exact contravention of the Kelvin statement of the second law. So now we have proved that if you violate Kelvin, you're also violating Clausius, and we've proved that if you violate Clausius, then you're also violating Kelvin. And that is the end of our proof. We have proved that these two situations are perfectly equivalent. If one is true, the other has to be true. Or rather, if one is false, the other has to be false. So that's the end of this formulation of the second law. And like I said, when the second law was first discovered, first formulated, it was so people could make discoveries about these types of heat engines. And this is the direction it went for a long time. And in the next video, we are going to look at Clausius' theorem and how the idea of entropy first came about with regard to this kind of heat transfer. And we're going to do that before looking at the statistical mechanical definition of entropy, which we will come on to and is really beautiful and lovely as well. But I just wanted to make a quick point about the nature of a concept like entropy, because nowadays we are really tempted to say that entropy is this, and that this statement of entropy is the most fundamental one. And a lot of people really like the statistical mechanical one, a lot of people really like the information theory definition of entropy. But what I put forward is that there is no one definition of a concept like entropy. A concept like entropy is like a cathedral. You have to see it from many different sides and many different visages in order to get a sense of the concept as a whole. It's such a confusing idea, it's such a wide-ranging concept with so much applicability in different areas that you really need to see entropy from 2, 3, 4, 5 perspectives. You need to understand how the idea came about and how it was developed in different fields. And I think it's really useful to see it from this point of view first and to understand the kind of ideas of heat engines that were first formulated, because it gives us a really good insight into that nature of the concept. And that's the main point I want to get across, that you should never be satisfied with looking at one definition for such a fundamental concept like entropy. And I include that also for ideas like energy or space and time and these kind of things. In order to get a really good essence of what the idea is actually all about, you have to look at it from as many different angles as possible, and you have to approach it with as many different techniques and in as many different ways as possible. So anyway, that ends the preaching part of today's lesson. Like I say, in the next lesson we're going to look at Clausius' theorem and how entropy was introduced into this law of thermodynamics. And then after that we're going to get on to some other ideas, and we're working towards Boltzmann distributions and the kinetic theory of gases and those kind of things. Oh, we're also going to look at Maxwell's demon, which is a really fun thought experiment about entropy. So we have a lot of great stuff coming up. Can't wait to go through it all. See you soon.